Generally speaking, I find people really like L'Hopital because it's like, oh, it's the nice way to take a derivative of a fraction. Take the derivative of the top, derivative of the bottom. And it's like, oh, just take the derivative of the top, derivative of the bottom, and you keep going until you get an answer. It's like, life is good. All right, well, since I don't see any questions, we can do our review problem, which, is about L'Hopital. So it says, let f of x be a twice differentiable function, and we're told that the limit as x approaches 2 of x squared f of x plus 4 divided by x minus 2 squared equals 3. And we're asked, what is f double prime of 2? Now notice here, we're not asked to find the limit. They give us the limit. We have to say, oh, based on knowing what the limit is, we can tell you something about the function. So there's some options here. So there's negative 3 halves, negative 1, 0, 1, 3 halves. Is there an answer? How about an intermediate step? If people started working on this problem, did you find out what does f of 2 need to be? Not f double prime 2, just f of 2. What does f of 2 need to be? Well, let's talk about it. Okay, so the answer is C, 0. What's going on? Well, you plug in 2. Whenever you're faced with a limit, the first thing you do is let's plug it in. That's your first reaction. You should always do that first. And you say, oh, this is bad news. I have a 0 downstairs. But we know that there's a limit. So it says, well, if there's a limit and there's a 0 downstairs, I have to have a 0 upstairs. Because if it's not 0, it means things are blowing up, heading off to some kind of infinity. The limit does not exist. But I know the limit exists because it told us to it. So that says we need the upstairs to be 0. So 4f of 2 plus 4 needs to be 0. So that forces f of 2 to be negative 1. Say, okay, now we know what f of 2 is. It's negative 1. We have 0 over 0. We push L'Hopital. Say, all right. We get this expression because we can do a product rule. Derivative of 4 goes away. That tells us 4f of 2 plus 4f prime of 2 over 0. Let's plug it in. Again, it's got to be that the upstairs has to be 0. Otherwise, it's hopeless. But we already know f of 2 is negative 1. So that forces f prime of 2 to be positive 1. So we say, okay, good. Now we're 0 over 0, so we have hope. We pushed it one more time. Do L'Hopital a third time. And at this point, we're like, game over, man. Game over. Because there's a 2. And what's true about 2? It's not 0. And so as soon as we have something that's not 0 over 0, we're done. So we say, great, plug it in. We know what f of 1 is. We know what f of 2 is. We know what f prime of 2 is. We don't know what f double prime of 2 is, but we do know what the limit equals. And then we can see that, lo and behold, the only way that could be true is if f double prime of 2 were 0. So the answer is 0. All right. Fun times. Any questions? All right. This is a more subtle one. L'Hopital. Oftentimes you're like, just keep taking derivatives, life is good. But it's good to understand why, the machinery. All right. So, today's thought for the day. The road to wisdom. Well, it's plain and simple to express. Err and err and err again. But less and less and less. And I think this is appropriate around the time we start getting exams back. And you get your exam back, and oftentimes it's frustrating. You wanted a higher score. Well, we also wanted you to have a higher score, so at least we're all in agreement. That's good. But just because you don't have a perfect score doesn't mean you're not learning. You're gaining experience and practice. And one of the things that tests do is it helps draw your attention to mistakes that you're making, your errors. Errors are a part of learning. Errors are a part of life. And so we don't have to be like, I made an error. I need to hang my head down in shame. It's like, I made an error. Oh, that's life. But now I want wisdom. So I'm going to learn from my errors. And that means looking at what you did, thinking about why you did that, and then saying, okay, that was a mistake, but now that I see that, I'll work on making that mistake less often in the future. I'd like to say, you'll never make that mistake again, but that's hard. That's a very high hurdle. And more realistically, I'm much more likely to make fewer mistakes than to make no mistakes. All right. By the way, you might recognize this. Pete Hine. This is the second time we put up a thought from him. He wrote a series of books called Grooks. And they were basically short poems and very pithy. And his most famous Grook, and I don't know it exactly, but it goes something along the lines of the following. Losing a glove feels bad, but not as bad as losing a glove, throwing it away, throwing the other one away, and then finding your first glove again. And so there's a wonderful story about that poem, which doesn't sound that interesting, but if you look it up, it's a great story. All right. So today. Well, one of the things that you can think of happening is we did, in the last lecture, we talked about L'Hôpital. And L'Hôpital was an application of derivatives. So we're in our applications of derivatives. And so we're going to do another application of derivatives, which is called Newton's method. And it's not so surprising that, given that a derivative is involved, we call it Newton's method. Now the goal here is to approximate solutions to f of x equals 0. Now, if you're wondering what does that mean, well, if you're sketching, what we mean by f of x equals 0 is we're trying to find what we have our roots. This is where f of x equals 0, where it hits the axis. We want to find that root exactly. Well, the problem is that's usually hopeless. Hopeless. Even for polynomials, once you start getting degree 5, it's pretty much hopeless. Say, okay, so finding it exactly, not going to happen. But can we approximate it? In other words, I don't have to be perfect. I just have to be good enough. If I'm an engineer, 4 digits of precision, and life is good. All right, so that's our goal. Can we approximate a solution? Can we get close enough to this root? Now, what's our sort of overarching plan? Well, the overarching plan is you make a guess, and it's probably not a good guess initially, but we say, let's take our current guess and make a better guess. And say, okay, so that's our plan. How do we turn a guess into a better guess using our tools? So we put on our sort of thinking hats. We say, okay, what's easy? Now, I said we're after roots, where f of x equals 0. What's a function where it's easy to find roots? What? Parabolas are, they're mildly easy, but I think there's something even easier. What's even easier than a parabola to find roots? Linear, aka lines. And we say, idea. This is sort of our very common idea that we have in Calc. Lines are easy. And so we oftentimes say, well, if we can just figure out what to do with lines, then maybe we can figure out how to turn that and get that into other functions. So we have our generic picture. So here's our x-axis, and we have some curve. This is our goal. It's our root. And unfortunately, we're not quite there. Maybe we guessed here. This is our current guess. So we say, all right, now you'll notice it is a line, but it's not bending too much. And it's a function. It's not a line. But we say, okay, what are we good at? What can we do? And remember, our theme is lines. What can we do? Use our favorite line. What's our favorite line? Y equals x? No, that's not it. The tangent line. So, idea. We have our guess. We can use our guess and say, let's find our tangent line. So this is our tangent line at the current guess. Now what's true? Well, the tangent line is a reasonable approximation to the function. So the idea is, wherever it crosses, that's going to be closer to our goal. So we'll follow our tangent line. And here, this will be our better guess. I'm putting better in quotation marks, but really we're just going to say, we'll take our current guess, run this procedure, and we'll get what should be a better guess. Okay, so let's talk about this, how it actually works. Okay, this is great and all, picture-wise, but rubber meets the road. Let's call our function y equals f of x. Let's say our current guess is at x equals a. What's our tangent line? Do you remember the formula for a tangent line? I'll give you a hint. It starts as y equals f of a. Ah, excellent. I love it. F prime of a, x minus a. All right. Now, lines are easy. So the question is, how do we find this part? Well, what's true about where our new guess will be? Y equals 0. So, at our new guess, we'll have 0 equals f of a plus f prime of a times x minus a. Well, we're trying to get x. That's our new guess. So we do a little bit of moving things around. For instance, you can say that f prime of a times x minus a is equal to negative f of a. You can divide, say x of a is minus f of a over f prime of a. And then you can add and say, aha, our new guess says take your old guess, subtract the ratio of the function at a divided by the derivative at a. So that's the idea. So it's just we're taking the tangent line at our current guess and figuring out where it hits the axis, and that's our better guess. Now, that's a better guess, but it's not the answer. What can you do? Do it again. So we can, let me try to change colors here. Go up, find a new tangent line, make a new guess. But that still may not be enough, so what do? Do it again. And what's going to happen is we're going to start forming points which should, in an ideal scenario, move closer and closer to our goal. And so this is a helpful way to approximate solutions. So that's our generic idea. Okay. So, now you might say, why do you keep hedging your bets? Why do you keep saying, well, it should, it might? Do you see anything that could happen that might make you say, that would be bad? See, yeah, you have a division here. So what would be bad? Well, what if you were saying, here's my root, and I'll make my guess over here? Then you're going to end up shooting, you might end up very far away. So instead of getting closer, you're getting further away. So things can go bad. And so it's not a foolproof system. However, if you start reasonably close, and oftentimes if you're looking for a root, you have an idea of where it is. If you start close to your root, this will usually almost always find your root. All right, so the actual procedure. So we're going to have a sequence of guesses. So we're going to indicate this by using subscripts. So x sub 0 is our guess at 0. It's our initial guess. It's almost always given to us. And we say, all right, then we're going to have our guess after one round. We'll call that x1. And our guess after 2 rounds, we'll call it x2, and so forth and so on. Now, how do we find our new guesses? We feed them into that formula we talked about. So to find our new guess, that's why you see this xn plus 1. That's equal to our old guess minus this ratio of the function at our old guess divided by the derivative at our old guess. This is called a recurrence. And a recurrence is a machinery that lets us say, okay, if I know what's happening at one step, what's happening at the next step. So we're feeding it through the machine. So we run it and we stop at some point. Now, where do we stop? Usually, because we don't allow calculators, and there's some notes, you'll notice we say, this is highly computational, because it is. Computers love this. Humans, not so much. In practical terms, because we don't allow calculators, we'll ask you for like x2 or x3. Just enough so that we see that you understand the process. We want to make sure you understand the process. So a couple of things to note. Remember, we're not finding the exact value of the root, just a good approximation. If you run it several times, it's a really good approximation to the point where your calculator wouldn't be able to tell the difference. When it does converge, it may not be the root you wanted, so make sure you start nearby, and occasionally things can go very bad. But that's not for us to worry about. What we want to make sure you can do is work through the procedure. Can you set up the recurrence? Can you use the recurrence to find a few terms? All right. So, any questions? Okay. So let's start with a very classical one. And when I say classical, I'm talking thousands of years ago. So let's approximate square root of 2 using Newton's method. Now let's go through and, method. I can spell method. No, I can't. Newton's method. Starting at x0 equals 1. Okay, so we're going to work our way through that. Okay, so we want to approximate square root of 2 using Newton's method. And people have been after the square root of 2, like I said, for thousands and thousands of years. And it was known to high degree long time ago. Basically using what we're going to talk about. Okay, so first off, if we're using Newton's method, we have to channel what Newton's method is about. We say, okay, we see Newton's method here. We say, well, that means what? That means we need to be finding roots. So, our estimating roots. But the key here is we're after roots. So, we say, in order for us to use Newton's method, we need to have a function. We have to find an f of x so that when you plug in root 2, you get 0. Because that would make root 2 a root. And then we say, okay, great. Now I can find that root to high precision using the method. So it didn't give us the polynomial. Oh, spoiler alert, polynomial. If you want, you can pretend I didn't say that. It didn't give us the function. We have to figure out what the function is. So, is there any good function where f of root 2 equals 0? So you plug root 2 in, out comes 0.
X squared minus 2.
X squared minus 2. All right. We have a candidate. Does that sound good? Yes. Yeah. That sounds good. Now I might say, well, wait. What about, say, this function, f of x equals x minus square root of 2? I plug in square root of 2, out comes 0. Why not use this function? Well, in order to use this function, what do you need to know? You need to know square root of 2 to use this. So you can't really use this function because you don't know square root of 2 yet. So this would be a terrible function. Now, x squared minus 2 is not the only function, but in some sense it's the simplest function. All right. So I should X this out. Don't use that. All right. Don't use. I don't know how to mark don't use. All right. Well, so once we have our function, next thing is set up our recurrence. So what's our recurrence? We can memorize the formula. If you want, just memorize how to derive the formula. But we should know it. Okay, so for us, what is f of xn? Well, what is f of x? F of x is x squared minus 2. What is f of xn? xn squared minus 2. So how do you plug things into functions? This says, whatever you put into me, square it, subtract 2. I say, okay, I'm going to put xn into you. Say, oh, okay, then take xn and square it and subtract 2. What about f prime of xn? Whoa. We should check. What is f prime of x? 2x. So what's f prime of xn? 2xn. Okay, now you can leave this as is. You can also try to simplify it. Do you have a preference? Leave as is, simplify? So I'll show you what we mean by simplifying. This is the same as xn minus. I'm going to divide the terms separately. So xn squared over xn leaves you with a single xn on top over 2. Now if you cover up the xn squared, minus minus makes a plus. And you'll see there's a 2 over 2. So that's a 1 over xn. So this equals xn over 2 plus 1 over xn. So xn plus 1 is xn over 2 plus 1 over xn. You can use either form. Okay, so we've only set ourselves up for success. We actually need to do the work. All right, well, let's start. I have a lot of blue pencils today. x0 is 1. How do we know x0 equals 1? Yeah, it tells us. What is x1? Okay, let's suppose we go here. It's 1 over 2 plus 1 over 1, also known as 3 halves, or for engineers, 1.5000. Okay, now, is 1.5000 a better guess than 1? Yeah, it's a little bit better. Okay, what about x2? What will that be? Now, again, I'll use this format just because it's a little bit easier to work with. So you'll get 3 halves over 2, also known as 3/4, plus, flip it, 2/3. And that's a common denominator of 12. So that's 9 over 12 plus 8 over 12, which makes 17 over 12. Okay, and 17 over 12 is something. It starts as 1.4. Let's do one more. What's x3? Okay, 1/2 xn. So in other words, I'm plugging in x2. 1/2 of 17 over 12, 17 over 24, plus 1 over that, 12 over 17. Well, okay, that's 17 times 17. Why did I think this was going to be fun? Okay, so that's 170 plus 70 plus 49. That's 289. 12 times 24, that's just, well, of course, the pun is too gross. You get it? It's too gross, right? 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 288. They might say, why is that funny? A gross is a dozen. And so 2 gross would be 2 times a dozen. And, okay, 24 times 17 is again a number. 540. Okay, no, hold on, I should do this right. This is 240. That's 24 times 10. And then 7 times 24, 140, 168. So that gives us something over 408 downstairs, and upstairs it's a 577 over 408. Does anybody have a calculator? And can we check what that is? 577 over 408? 414. More digits? 2156. 2156. Okay, so that's x3. Since you have a calculator, what's square root of 2? 1.41421356. How close are we?
Very.
That's, for coconut technology, we've already gotten it so precise that an engineer would say that is square root of 2. And we didn't take multiple pages. So that's pretty quick. So it turns out Newton's method can go there fairly quickly. So that's the idea. Should we try another one like this? All right. We'll do the same flavor. Okay. use Newton's method to approximate and something like a square root. Something that we can compute, like a cubed root, a fourth root. And we can stay with square roots. Sorry, what? Square root of 3? Okay, all right. All right, square root of 3. Starting at, well, what's close to square root of 3? Usually you should start close. Should start at 2. Yes? All right, so I haven't done this before, so I have no idea what will happen. So if you're asked a question like this, say, okay, Newton's method is about roots. So first thing is, what's the function we're trying to find the root of? So this is our root. What's the function? X squared minus 3. So because we stayed with the square root. Well, if this had been a cubed root, it would be x cubed minus 3. If it had been a fourth root, it would be x to the fourth minus 3. All right, so we're after x squared minus 3. We want the root. And then this is our initial guess. Okay, so set up your recurrence. Xn plus 1, xn minus f of xn over f prime of xn. We'll put some notes here on the side. F of x equals x squared minus 3. Now you might say, what if I'd chosen 3 minus x squared? Would it still work? Yes? No? What do you think? If you chose 3 minus x squared versus x squared minus 3, will it still work? Yes. Would anything change? No. You might say, wait, why not? Because if you multiply by a negative for the function, you end up also multiplying the derivative by a negative. And two negatives are positive. They cancel each other out. Okay, so f prime of x, again, 2x. So our recurrence is xn minus, what goes upstairs? Xn squared minus 3, and what goes downstairs? 2xn. And we don't have to simplify this side. We'll do it without simplifying. Okay, so let's try to get to at least our x2. So x0 is 2. So x1. So when you're after x1, think about it as n equals 0 here. So that's saying, that's like x0 subtract x0 squared minus 3 over 2x0. That's what the recurrence is telling you to do. And it's just like, but I know what x0 is. So that becomes 2 minus 2 squared minus 3. So that's 4 minus 3 over 2 times 2, which is 4. Okay, 4 minus 3, 1. So it's 2 minus a fourth, which is 7 over 4. Because 2 is 8 fourths. 8 fourths subtract 1 fourth is 7 fourths. And I know how to do this for the engineering students. That's 1.7500. And that is closer to the square root of 3 than 2 is. All right, so I said we'll go for x2. Okay. x2. Now, that means here we're plugging in n equals 1. So that's the saying we want to take x1 subtract x1 squared minus 3 over 2x1. So make sure you put everything in the right place. I will tell you personally, this is a place where I often make a mistake, is I forget to put the right number into that first part. So 7 fourths subtract 7 fourths squared minus 3 over 2 times 7 fourths. Well, it's times like this I regret saying let's figure it out. But let's figure it out. 7 fourths minus, 49 over 16. That's what you get when you square 7 over 4. Subtract 3 over, and 2 times 7/4 is 7 halves. Because you can cancel a little bit of the 2's. So 3, what's another way to think of 3? 48 divided by 16. So you have 49 over 16, subtract 48 over 16, which gives you a 1 over 16. So that's 7/4 subtract a 1 over 16 and a 7 over 2. Okay. Well, that's the same as 7/4 subtract 1 over 16 times 2 over 7. Okay, so you can at least get a little bit of cancellation. So let's suppose you wanted to add these fractions. Here you got 4. Here you have 56. 8 times 7. What's your common denominator? 56, because 4 is divisible by 56. So you have to multiply the first one by 14. 14 times 4 is 56. So you have 14 times 7 over 56, subtract 1 over 56. Well, 14 times 7 is a number. It's 98. 98 subtract 1 is 97. And now like, but 97 divided by 56 is 97 divided by 56. Yeah, they don't have any common factors. Okay, so this one I don't know. Does anybody know what this is decimal-wise? 1 point. I do agree with the 1 point. 7.3. Do you have a few more digits? 2. Okay. Maybe what? One more digit? 1. Okay. What does square root of 3 equal? How did we do? 1.7320. Okay, so for an engineer, it's not exactly the same, but it's close enough. Now, would you want to keep going and find x3 in this case? Why not? Well, because we don't want to. Yes, that's a good reason. But if you were to find x3, you would have to square that. And that doesn't sound like fun. But computers, they love this stuff. They're like, this is the reason I was born. All right. So, your turn. Use Newton's method to approximate a root to y equals x cubed plus 7x minus 3. Starting with x0 equals 2, give the exact value of x3. Now, if you see that you have the exact value of x3 as your goal, what should be true about numbers like x1 and x2? They should be relatively simple, because we're not going to ask you to do something crazy if you can't run the computation in time. So there's sort of a check. If we ask you to find x3, x2 needs to be pretty simple. So if you get to x2 and it's not simple, mistakes were made, or there's more simplification for you to do. Who found x1? What did you find? 1. Good. Who found x2? A half. All right. And x3, 13 over 31. So again, the procedure, set up the recursion, and it's just a matter of plug away. And just be patient, take your time. Any questions? Okay, so quick notes. What if you're not asked to find a root? you're saying, here's a problem. We won't go through it completely, but let's talk about what if you want to find where two functions cross, where f of x equals g of x. Can we use Newton's method to do that? And if so, how do we do it?
You said x equal to 5 plus 5x.
Well, that's what we're trying to solve. X cubed equals 5 plus 5x in this case. But in general, can we use Newton's method? And if so, how do we do it?
Turn the two functions into one function that's equal to 0, and then solve.
Yeah, so essentially this is the same as saying find f of x minus g of x equals 0. And then we're like, whoa, that's root. That makes us happy because we have tools. So it's really the same thing as finding the root, or estimate the root of the function x cubed subtract 5 plus 5x. So yes, you can find Newton's method to use Newton's method to find crossings. And a minute left. That's enough to take a stab in the dark. So suppose we give you a sequence and we say, look, it goes to something. We give you a sequence, we tell you where you start, and we ask you, what does it go to? What can you do? Now, I'll warn you, there is a distraction here. Does that really matter? No. It's not about the initial value. It's about where you're going. So what's the answer? Any guesses? D.
Dude, I told you.
Because the idea is, hey, make it look like Newton's method. And once you make it look like Newton's method, the function is x to the 5th minus 15th. So that's where we're looking for our root.